This is Pre-Calculus, the lesson for 7-2 Day 1. We're going to start talking about matrices today, which are a very cool way to organize numbers, generally used for large sets of numbers that need to be used in any calculation. So what we want to be able to do for our objective is find the order of a matrix, add and subtract matrices, multiply a scalar and a matrix, find the identity and inverse of a matrix, find the determinant of a square matrix, use a calculator to compute values with matrices, and apply matrices to model and solve real-world applications. Probably won't get through everything today, but we'll get a good start. So what is a matrix? Well, a matrix is a rectangular array of numbers. Matrices can be used to solve systems of equations and record data. And so what we see when we look at a matrix is a grouping of numbers. I'll just throw a bunch of numbers down here. Like so. And so I have the numbers 0, 1, 7, 2, 3, 9, 4, 5, 11, and that's a matrix, and those numbers would all represent some quantity. So the definition of a matrix that we see in the box here is let m and n be positive integers, and m by n matrix. And the x, of course, we don't necessarily like that happening when we're talking about math because we don't want people to confuse x with multiplication, but this is an m by n matrix. Just like if you're talking about a 2x4 at Menards, it stands for that by piece. And that's a rectangular array of m rows and n columns of real numbers. So you can see in the blue one that I made up here that I have rows and columns. Now rows are going across. And columns, you can think of the columns like the columns in front of the White House. These are the columns up here. So rows side to side, really. Thinking about like the horizon, that would make rows. And then columns in front of the White House generally helps people figure out what's going on. So when it says an m by n matrix, what we want to do is find the rows by the columns. So for mine, there are 1, 2, 3 rows and 1, 2, 3 columns. That would be a 3 by 3 matrix up there in the blue. And the matrix is as large or as small as you need it to be for the numbers that you are collecting. Now, when you look at this matrix that they have in the green box here, what we see is they have this little subscript notation 1, 1. So you think, well, what on earth does that mean? Well, the first subscript tells you the row, and the second subscript tells you the column. And the lowercase a is just for the entry. So it's the entry in the first row and the first column. So the entry in the first row and first column for my blue matrix up here would be 0. So A11 would be 0. But now I can't use A sub 1, 1 to get this 5. To get this 5, I would need row 1, 2, 3 and column 1, 2. So 3, 2, the entry in that position, would be a 5. And that notation that we see down here is shorthand for whichever entry you want to talk about. So the problem arises with matrices if there are several repeats of the same number and you want to point out to another person a particular number. If there are multiples of that number, you're not going to know which one unless you have a little matrix vocabulary and you can say it's the entry in the second row, the third column, and then people will know exactly what you're talking about. So little vocabulary about matrices. Then each element or entry, which again is A sub, and they're using I and J. That might be a little hard to see. So A sub ij, and the I is the number of rows, so that's the subscript for the rows, and then the j is the subscript for the columns, so that gives us a way to describe each element that's in the matrix. So the element A sub ij is in the ith row. I know that's really weird to say the ith row, but we just needed a variable to stand for it. And then the jth column. So it's always rows, then columns, whether or not we're trying to give an order to the matrix and say it's a 3 by 4, or if we're trying to find the entry for the third row, fourth column. So rows, then columns. Example 0 down here. Scoot this up. Says identify the element. So basically we want to give them the number that holds this position. It says identify the element specified for the following matrix. So I look at A sub 1, 3. That tells me that I need to go to the first row, but then the third column. Well, here's the first row. And this is the third column. So A sub 1, 3 is going to be -1. And then I start over. So let's go to B. B says A sub 3, 2. So third row, 1, 2, 3. There's the third row. Second column, 1, 2. That's the one right there. That's in the third row in the second column. -4. Go back again. And C says, how about the fourth row, third column? 1, 2, 3, fourth row, third column, 1, 2, 3, third column. And that is the entry in the fourth row, third column. Now, I've found this a couple of different ways, but always notice how I'm marking is rows by columns, trying to figure out which row am I at and which column. And then row 2, column 3. So row 2, column 3, 1, 2, 3. There it is, -5. So rows going across, columns up and down in that vertical nature. Rows horizontal and columns vertical. And that's just finding elements, and hopefully you'll have a couple of those in the homework, but not too many because that's pretty basic, just figuring out the rows and the columns there. Determining the order of a matrix. This is where we want to say it's a 2 by 4, it's a 12 by 2, whatever the order of the matrix is. So what we have to do is figure out rows by columns. And this says the order of an m by n matrix is m by n. That's what it is. And if m happens to equal n, well, that makes it a square matrix if it's 2 by 2, 3 by 3, 4 by 4, 5 by 5. And those matrices are special. There's a lot of math we can do with square matrices, so we like those. Two matrices are equal matrices if they have the exact same order and their corresponding elements are equal. So not only are they the same size, and that's what the order really means, they also have the exact same elements in the exact same positions. So looking at A, if I want the order of this matrix, what I need to notice is it has 2 rows and 1, 2, 3 columns. So that is a 2 by 3. And yes, we use an X to stand for the by for matrices. And then the next one, 1, 2, 3, 4 rows, 2 columns. That's a 4 by 2. And then 1, 2, 3, 1, 2, 3, 3 by 3. So order is just how many rows does it have, and then how many columns does it have. And there's going to be some math that we can do with matrices that have the exact same size. There's going to be some math that we can do with matrices that have different sizes. And in order for us to tell whether or not we can actually do the math, we need to know what the order is. That's usually your first step when you're working with matrices and you want to perform some kind of an operation on it. Addition, subtraction, multiplication is to check for the order. So matrix addition and subtraction, we can add or subtract matrices of the same order. Notice that. They have to have the same order. And that's because we're going to add or subtract their corresponding entries. So all you do is figure out first row, first column, add it to first row, first column in the second matrix, and then go on to the next position. So maybe it's second row, first column, and second row, first column. And you just use that method as you add or subtract. Matrices of different orders, basically it means they have different sizes. You cannot add or subtract those because you have to have the same entries in the same positions in order for that to work. Which, what I mean by that is, if you have a 2 by 3 matrix, you're going to have another 2 by 3 matrix so that each position that's held in the first matrix has a corresponding entry in the second matrix. So matrix addition and matrix subtraction, we see a definition here. And again, what they're doing is they're showing us, we're just going to do this really generically. We're not going to put numbers in there for the order. We're going to say some entry A sub ij and B some entry B sub ij are matrices of order m by n. Now they have the same order, so you can go ahead and do the addition. And what they're showing us is if you want to obtain the matrix A plus B, what you have to do is add those corresponding entries. So all the entries A in the first matrix get added to all the corresponding entries B in the second matrix. And the same thing with the difference here, but what we're doing, of course, is subtracting if we're going to talk about difference. So corresponding entries. All right, so now we get to it. Let's take a peek at these. Add, subtract matrices. Well, the first thing that has to happen for us to add or subtract matrices is we have to have the same order matrix. So with this one, we have 1, 2, 3 rows and 2 columns. So this is a 3 by 2. There we go. And we need to have another 3 by 2 to add that to. 1, 2, 3, 3 rows, 1, 2 columns, 3 by 2. So we'll be able to do this math. And all we have to do is add corresponding entries. So first row, first column, 3 plus 0, those two get added together and we get a 3. Then we have first row, second column, and let me do a little bit of changing the shape here so you can see which one goes with which. So 6 plus -1 is 5. Then I'd go down to the next row. So second row, first column, -1 plus 6, and etc. You know, you can continue on. So -3 plus 0 is -3, -5 plus 2 is -3, and -1 plus 3 is 2. And notice they end up in the same position in your final matrix. So those positions get added together for each one of those matrices and gets placed in the same position. So when you add row 1, column 1 to row 1, column 1, you get your answer to row 1, column 1. So there's our matrix, 3, 5, 5, -3, -3, 2. Let's go to B. 2 by 3. 2 by 3. We can do the subtraction. And again, what we do is we just look for the corresponding entries. So -5 minus 6 will be -11. 2 minus a -5 will be 2 plus 5, which is 7. -2 minus a -6 will be -2 plus 6, which is 4. 4 minus 1 is 3, -2 minus 3 is -5, and 0 minus a -3 would actually be 0 plus 3. So our resulting matrix, -11, 7, 4, 3, -5, 3, is also a 2 by 3. You know, it stays that same size. And that's why it was so important that we had the same size for all of these to begin with, because we need those entries to match up. So we take a look at C and we should know something's up. Well, in this first one, we have 2 rows and 1 column. So that's a 2 by 1. In the second one, it is 1 row and 2 columns. We can't add those. We don't have corresponding entries for this one. So what we would have to write down for this is cannot be added. They have to have the same order for us to be able to add and subtract matrices. So again, the order, no matter what we're doing, we're going to care about what the order of the matrix is. Next page. Matrix A gives the mean SAT verbal scores for the 6 New England states over the time period from 2001 to 2004, and it gives us the source there. Matrix B gives the mean SAT mathematics scores for the same 4-year period. So 2 parts to the SAT. You have the verbals and then you have the mathematics. And what we want to do is express the mean combined scores for the New England states from 2001 to 2004 as a single matrix. So we have all of this, and what we would want to do is just go through and find A plus B, because if you add the verbal score to the mathematics score, you will get that final SAT score. So in class, what I would have you do is have one row of students add the first column to the first column. So first column in A to the first column in B, and then in the next row the second column and the second column. And if you want to, you could stop the video right now and go ahead and do that addition, but let me just talk you through it here. So we'd take the 509 plus 510, and that would give us 1019. And then it doesn't matter which direction you go. So some people always like to go by rows first. So 509 plus 509, 1018, 512 and 514, 1026, 515 and 515 would be 1030. And then you just continue on, go after the second row, adding those corresponding entries, then third row, fourth row, etc. So let me show you what the final would be here. We'd have 1006, 1005, 1004, 1006, 1026, 1028, 1038, 1041. Next row, we'd have 1036, 1038, 1043, and 1043. And then we have row 5, 1000, 1007, 1006, and 1005. Then we'd have 1017, 1022, 1027, and 1028. So those would be the overall scores with the verbal and the mathematics scores all together here. And you can see that they have these matrices designed, if you go back up to the beginning here, by individual states. So they ordered them according to states, and then years. So this is an organization of numbers. They just didn't pop out from somewhere. They decided to organize those by state and then year. So obviously that's not difficult. It's just kind of putsy. You have to go through and add those individual entries as you go through there. So what's next? I mean, that can't be the only thing we're going to do with matrices, and it's not. And one of the things we're going to do is we're going to use scalars. Scalars you first heard of in geometry, and that was when you were talking about dilations, either making something bigger or smaller based on a scalar. And that's just going to be multiplication. So the product of a real number k, which is going to be our scalar, and an m by n matrix, which again we see our entries as the ith row and the jth column, is the m by n matrix that you get when you multiply by that scalar. So all you do is take each of your entries and multiply them by the scalar. So each and every entry that you have gets multiplied by that scalar. And that matrix is called a scalar multiple of A. So you just take every single entry and you multiply it by the scalar. So in this one, we have a 2 by 1 matrix, and we're just going to go ahead and multiply those entries by 5. So 5 times 4 is 20, and 5 times 3 is 15. So we get the little matrix 2015. And then The next matrix we're supposed to multiply by -5. Now you may have noticed I'm not checking the order of the matrix here, and that's because you can multiply a scalar times any size of matrix. The order doesn't matter. So -5 times -3 is 15. Anything times 0 is 0, and that's really small. So that should be a -25 down here. So 15, 0, 0, -25. And then we have another scalar, and this is a 3 by 2 matrix here, but again, we don't even need to check that. I'm going to make this a little bigger though, because I felt like I was really getting squashed in that last one. Everything multiplied by 5. So 5 times 5 is 25, 1 times 5 is 5, 5 times 1 is 5, 5 times -2 is -10, 5 times 1 is 5, and 5 times 2 is 10. So there's our matrix: 25, 5, 5, -10, and 5, 10. So far, so good. Doesn't seem like these matrix things are very hard at all. You know, if we can figure out what the order is, we can add them, we could subtract them, we can multiply them by a scalar. That's not a big deal. So what's next? Well, this one says we're going to use that scalar multiplication. A consumer advocacy group has computed the mean retail prices for brand name products and generic products at 3 different stores in a major city. So I can see that right here. Store A, B, and C. Now, it says we've got the products that are brand names and then generic. So generic is the one that's, you know, not special. It'd be like if you go in and buy a bottle that says Aleve on it, that's a brand name. You're going to pay a little bit more money than if you were to buy the generic, which will just be naproxen sodium. So most people experience their first learning of generics with medications because the price is much lower with those generics. Now this says the prices are shown in this 3 by 2 matrix, and we can see that there's the brand names and then there's the generics. And it says the city has a combined sales tax of 7.25%. So they are taxing their pharmaceuticals. And what we want to do is construct a matrix showing the comparative prices with the sales tax included. Well, this all starts with realizing just because you're paying the sales tax, it doesn't mean that you're not going to pay for the product. You have to pay for 100% of the cost of the product, plus you have to pay that 7.25% tax. So that's really going to be 107.25%. But if we want to do any math with that, we know that we have to change percentages into decimals. So this would be 1.0725 as a decimal. And that's what we would want to multiply all of those prices by that we see up there, because that will give us 100% of the cost of the medication or whatever it may be. In addition to that, it will give us the 7.25% tax. So what we really have to do is multiply the matrix that they gave us by the scalar 1.0725. And why don't you take a second and do that, and then I will put the answer up here so you can see if everything has come out correctly. While you're doing that, I will go ahead and just relabel this again. Usually there would be follow-up questions with this, so we would want to have things labeled. All right, so hopefully you've already got those punched in. If not, you can pause this baby. So 1.0725 times 3.97, $4.26. 1.0725 times 364 is $3.90. Then we need 1.0725 times 3.78, which is $4.05. 1.0725 times 3.69, $3.96. 1.0725 times $3.75, $4.02. Not liking that 4. There we go. And then 1.0725 times $3.67, $3.94. Now, thinking here about questions that you might have asked when I was in class. every once in a while, somebody wants to put straight lines on either side of the matrix instead of making those square brackets. Don't do that. And that's because the straight lines have a special meaning in matrices. They're used for determinants, and we'll talk about those a little bit later on. You have to have the square brackets to hold what you have in your matrix. So it's important to, do this, especially since you're learning it for the first time. Do it exactly as you see it up here. And now this would be the spot where they would say, okay, now you've got this brand new matrix, now tell me something about it. And we could say, well, with tax included, at store A, the brand name would be $4.26, but the generic one would be $3.90, and compare those and actually, have an educated chat about what's going on there. Next up, well, let's talk zero matrix. A zero matrix is an m by n matrix of 0 where all the elements are zeros. So we don't use those a whole lot, obviously. Matrices that consist entirely of zeros are not the most useful thing in the world. So 0 is the additive identity for all sets of m by n matrices, and that's because whatever matrix you have, if you make a zero matrix that has the same order, so it's the same size, and you add it to your original matrix, you just get that matrix right back. You haven't changed its identity. Identity is who you are. Matrix A, you are not going to change who matrix A is by adding zeros to it. It isn't going to happen, so it keeps its identity. The m by n matrix B, and notice this one has a negative in front of it, the negative A entry, ith row, jth column, consisting of the additive inverses of the entries of A, so basically the opposites of all the entries. That's called the additive inverse of A, not identity, inverse, because we want to know how do you undo this matrix by using addition. So the additive inverse means what would this matrix be so that when we add it to A, we would get 0. And of course we realized, well, what we would do is we would take all of these entries and slap a negative in front of them. So really, we'd have negative A, ith row, jth column for each one of those. And like it says, we could also write this as B equals negative A. So just negating, and really just a scalar of -1 times everything in A would give us the additive inverse. So every entry would be that way. Now, a little more complicated, we're going to talk about matrix multiplication. And multiplying matrices is not just an entry by entry process, so this takes a little bit more. To find the product AB of two matrices, again, they're sitting right next to each other, that means we're going to multiply. So this is A times B. The number of columns of matrix A, and that would be on the left side, must be equal to the number of rows of matrix B on the right side in order for you to multiply. Any row of A has the same number of entries as any column of B. Boy, oh boy, what are they trying to get at here? Well, if we have a 2 by 3 matrix, no matter what, the rows in the second matrix have to be a 3. That's the only way that we could multiply this first 2 by 3 matrix by something. Now, it doesn't matter what we have sticking out there at the end, because what matters with these is that this number of columns is matching this number of rows. And our answer will come from the two outside dimensions. So those two middle numbers have to match in order for us to be able to do the multiplication. And when we do, the resulting matrix will be this size. So let's see what it says here. In general, A is an m by n matrix times B, which is an n by p matrix. So notice the two n's match there. That's the only way we can do this multiplication. And when you do that multiplication, you will get m by p for the resultant matrix. So you want to write that order down right away for a couple of reasons. First of all, you have to make sure you can actually do the multiplication. And secondly, you'll know what the size, the order of your matrix result will be. So each entry of the product is obtained by summing the products of the entries of the row A by the corresponding entries of the column B. So this is where it gets a little tricky. This is one of those things where you have to train your brain on how to move in two different directions at one time. Because what we do is take the entries of the first row times the entries of the first column and add them together. So A times E plus B times G. So first row, first column. Then you would take the second row down here and you'd say, okay, I need the second row times the first column. So C times E plus D times G. And now that you're done with the first column, you don't need that anymore. And you go after the second column. So now we would use the F and the H and say A times F plus B times H. And that would go in this position, the upper right position, which would be first row and second column, because that's what we just multiplied to get that, was the first row and the second column. And then down below, we would take the second row and C times F plus D times H. And again, that will go in this position because this is the second row and the second column, and that answer will be the second row and the second column. So like I said, this is one of those things where we have to train our brain, because our brain has to look this way and this way at the same time. And usually the best way to do that is basically just using your fingers to set up which numbers have to be multiplied by which numbers in order to get it. So example 4 says, let's find the product of two matrices. And we're not guaranteed, first of all, that we could actually do this, because it says if possible. So I look at A and I see that I have 2 rows and 3 columns. So it's a 2 by 3. And then B is 1, 2, 3 rows by 2 columns. Well, that's good news. These 3's in the middle, they match. That means I can actually do this multiplication. And my answer will be 2 by 2. So different ways to actually do this multiplication. Like I said, some people will just use their fingers. That's going to be a little hard for me to show you here. But other people will say, okay, so now what am I doing? Well, I have 4 positions here. This position is row 1, column 1. So what I need to do is take the numbers in row 1 times the numbers in column 1 and then add them together. You just multiply them 2 at a time. So that would give me 2 times 1 plus 1 times 0 plus -3 times 1. And then add those results together. Well, 2 plus 0 is 2. 2 plus -3 is -1. So that is row 1 and column 1. Now, we go after the next position. And I think I'll go after this one next. That position would be row 1, column 2. So row 1, column 2. And again, 2 at a time, and then add them together. So 2 times -4 plus 1 times 2 plus -3 times 0. Well, we'd have -8 plus 2 is -6. -6 plus 0 is -6. All right, I want to make sure I have the colors matching here for what we're going to do next. So this position is going to be in the second row in the first column. So second row, first column. 0 times 1 is 0. 1 times 0 is 0. 2 times 1 is 2. 0 plus 0 plus 2 is 2. Last position that we have over there is row 2, column 2. Row 2, column 2. And don't be afraid, grab a pencil and do this if it helps, put those kind of oval shapes on there to get yourself organized. So we'd have 0 times -4, which is 0, 1 times 2, which is 2, 2 times 0, which is 0, so 0 plus 2 plus 0. And that would give us 2. So we have our little matrix -1, -6, 2, and 2. And we have it. There's our first matrix multiplication with all kinds of writing all over it. So let's go down to the next one. And with this one, again, the first thing we want to do is check that order to see if they're the same size. 2 by 3. 2 by 2. We can't do this one. The number of columns in the first matrix does not match the number of rows in the second matrix. So this is not defined. We're not going to be able to do this. So the product is not defined. Unable to do that one. You won't find a lot of those in the homework, by the way, but there'll be a couple just to get you started. Now, this says you try, multiply the matrices together. So it would be a really good idea for you to pause the video right now and give these a try. Now, as the matrices get bigger, it's a little harder to keep track of everything. So just try and do your best and see what you can do, and then I'll go through the multiplication with you. All right, well, let's see if we can even do this. 3 rows, 2 columns. 3 by 2, 2 rows, 2 columns. 2 by 2. We can do this math. We have 2's right here in the middle, and that's for the columns of the first matrix matching the rows of the second matrix. And in fact, the outside numbers here tell us we're going to have a 3 by 2 when we're done. So we can get organized here and say, all right, well, this is supposed to be a 3 by 2. So let's see. I'm going to take the first row times the first column, 2 at a time, and then add them together. 3 times -1 is -3. -1 times 5 is -5. -3 plus -5 is -8. Now we'll go ahead and go down to the second row. -3, 6. But we're still going to use that same first column. -3 times 1 is 3. 6 times 5 is 30. 3 plus 30 is 33. Row 3. -6 times -1 is +6. -6 times 5 is -30. So we have 6 plus -30, which is -24. And now I am done with column 1. So I have to go back and do column 2. Let me see, I'll just switch colors here and see if that helps you. So here's row 1, column 2. 3 times 6 is 18. -1 times 4 is -4. 18 and -4, 14. Go down to row 2. -18, +24. Then the last one, last row, -6 times 6 is -36. -6 times -4 is -24. -36 and -24 will be -60. So keep organized. You don't have to try to speed through it, but make sure you're multiplying them 2 at a time and then adding those results. All right, next one. D has a 4 by 2 matrix and a 2 by 3 matrix. So we're good to go. Those 2's on the inside match, and we're going to get a 4 by 3 matrix as our result. So definitely more to keep organized with this one. So let's see what we can do. Row 1, column 1. -4 and 12. That gives us 8. And we notice, well, this isn't going to be any harder math than the one that we just did. We had 2 to multiply together and then add. We just have to keep it organized. That's how these work. So row 2 and column 1, -8 and -6. Add to -14. 10 and 0. 8 and 12. and we have our first column for our resultant matrix. Resultant just means, you know, our answer as we're going through it. All right, pick a different color here. Done with column 1, go to column 2. We have 4 and 0, and that's 4. Then we have 8 and 0, and that's 8. Then we have, going to the next row, I probably better put the color there so you can see that, negative 10 and 0. And then the last one, negative 8 and 0. So we have that all organized. So there is our second column of this matrix, the 4, 8, negative 10, and negative 8. And let's go to that last column right here. Row 1, column 3, negative 4 and 18, and that's 14. Next row, negative 8 and negative 9, negative 17. Next row, 10 and 0. Next row, 8 and 18, 26. So our final column there, 14, negative 17, 10, and 26, and that makes up our matrix. So the color might also be helpful here too. When you first start out, there are just so many different ways that you can try and make sure that you're organizing your thoughts. Just find a way that works with you. And maybe you went through this and did column 1 with all the rows first from the other one. It doesn't matter. It's just whatever works for you and that you can consistently do it. Now that's the key. Do them the same way every time, because then it'll become a habit. It'll become natural for you to multiply matrices. All right, let's go to E. We have a 2 by 3 and we have a 2 by 3. Hey, they're the same size. Well, that would be absolutely great if we were adding and subtracting, but we're not adding and subtracting, we're multiplying. And those don't match. The columns of the first don't match the row of the second. So that means the product is not defined, and that's what we would write down. The product is not defined. We can't do it. Now, something we need to know about matrix multiplication is this, that in general, A times B does not give you the same answer as B times A, and that's because of the nature of multiplication. It's not as basic as just adding and subtracting entries. You know, there's more going on there. So that means matrix multiplication is not commutative. Matrix multiplication is not commutative. Now, we're not used to that. And that's because we've all learned that 3 times 4 is the same thing as 4 times 3. It doesn't make any difference which order you do that in. But remember, matrix multiplication is more complicated than that. You know, there's multiplication taking place, but there's also addition taking place. And so it doesn't work. And that means we can't just switch things around with matrix multiplication to make things easier on ourselves. It doesn't work that way. Now, this is probably where I would be able to get if I were in class with you. So I think I'm going to stop at matrix multiplication. So hopefully, as we've worked through this, you've thought, okay, adding and subtracting, not so bad. You know, I can find the order fairly easily. Adding and subtracting is not bad. Scalars, cool, not an issue at all. Matrix multiplication, yeah, I got to keep myself organized, and then you should be set with that. So this is the assignment for 7-2 day 1, and I'll leave that up there for just a little bit so you can take a peek at that and or pause the video. I just went ahead and checked the homework, and it looks like you should be able to do all of that since we made our way through matrix multiplication.